Good evening, ladies and gentlemen. Welcome to our December general meeting and star party. Our presenter tonight is Chanan Greenberg with his talk As Long as the Sun Shines, which may have something to do with tanning lotion, I'm not sure. It's the third in a series he's put together, two others of which we've enjoyed in August and October. Plus, he's promised us now a fourth one come January titled The Life Cycle of Stars. Hanan is longtime member of the club, joined back in around 2000, I believe, and I think he served 7 years in a row as our vice president. And though his work and his living arrangements took him out of our locality down to San Jose, he has recently returned to favor us with his presence, which for which we're very grateful because there are two other clubs, San Jose and Peninsula, that he could have gone to, but he chose to come back and favor us with his productions and his participation. Now, as long as the pandemic interferes with our customary face-to-face events, we expect to hold these combination meetings and star parties over Zoom and may continue to feature them even after our access is restored to CSM and Crestview Park, assuming everybody isn't just sick to death of Zoom. We've been finding it useful to hold our meetings and lectures on the Saturdays closest to first quarter moon, which is not only the best phase at which to observe the moon, but which, because it sets early, avoids having a bright moon in the sky during the following star party, when we're looking for fainter deep sky objects. Now you've been added, I believe, in a microphone muted condition when you first come in. I know I was. But if you have a question or contribution, feel free to unmute your microphone to say your piece. Then please again mute your mic to exclude background noise. There is a raise your hand button, I believe, if you wish to be recognized, or you can use the convenient chat feature if you have a comment to add. Let's see. Our lecture should take about 45 minutes, I would gather, to an hour. Following that, we'll have time for some Q&A. Then we'll move on to the star party, whose images will include lunar and planetary objects, most likely, as well as those of the deep sky. They will be accompanied by a descriptive live narration, which will likely run between 40 minutes and an hour, depending on how much demand there is from the audience. So welcome and thanks for joining us. Enjoy the program. Hanan, it's all yours.
All right. Thank you, Mike, for that introduction. There was a question that came up from Marianne earlier about where to look for Jupiter and Saturn right now in the sky. It's basically, if you're looking at the moon, you should be looking to the right and a little further down from the moon. It would be quite low in the sky right now, so you have some disruption on where you can find it. It's the best time to try and capture it is around 5:30 or 6 p.m. because it's still not terribly low in the sky. It's already pretty low and there's a lot of atmospheric disturbances. But, that would be probably the best time to try and see it. So tonight it might already start being a bit late because it'll start setting and getting to really, really murky views. And we still have 2 more days of it getting closer and closer. So you should try and use it. So,
thank you.
Sure. So having addressed that question, let's get started. Today's presentation is called As Long as the Sun Shines. And what we will be covering in today's presentation is a few topics. We'll talk a little about why does the sun shine and how long will it shine and how do we calculate the lifetime of the sun. As we go through this, we'll share some different theories of the different sources of energy that the sun could tap into and how we arrived at what we believe today is the correct model. And we'll finish off with a quick overview of the structure of the sun so we have a better understanding of how it operates. Before I go into the presentation itself, I'd like to take a moment here and say thank you and recognize Professor Richard Pogge from Ohio State University. I subscribe to his podcast, which I highly recommend, by the way. It is a series of podcasts of a series of lectures on Astronomy 101, Astronomy 102, which cover a whole list of topics. And this is one of the many presentations that I heard him give. And I found it so impressive and so engaging that I actually reached out to him and asked him if I could get a copy of his materials and use it for purposes like the ones that we're doing tonight. And he was kind enough to share with me his information. So roughly around 75% of everything you're going to see tonight comes from content created by Professor Poggi and used with his permission. But I just, first of all, want to recognize that, and also, again, recommend if you're looking for phenomenal podcasts that are quite engaging and easy to follow. I listen to them while driving for a couple of years, actually. They're really, really rich in content and very easy to follow. So with that, let's go into discussing how the sun works. Now, discussing the inner workings of a star is very, very difficult, because all we can observe is the surface area. We're looking at something which is only 1 part in 1 billion of the mass of the sun. So how can we talk with any authority about what's going on deep inside the sun? And there are a few things that we use to conclude what the right model is. First of all, we have a basic understandings of the laws of physics and how gas and matter behave. We can measure some of the external attributes of the sun. We can look at its radius, its mass, its luminosity. We can measure that luminosity, which you'll soon see is very important. And we can use that to theorize what is going on inside. And then, as you'll see later on, we can also create experiments to test those theories and find out which one of them is right. So we'll walk you through, obviously, all the details. Now, in today's presentation, we're going to touch on a lot of concepts. Some of them are more complex than others. So as Mike said earlier on, please feel free to come off mute and ask a question verbally, which is best, because I won't be tracking chat all the time. You can also send it into chat if you'd like, and we'll try and get to those as well. And after you're done asking your question, please go back on mute. So in today's presentation, we're going to answer one simple question: how long can the sun shine? And we will basically provide a number, but more importantly, we'll try and understand how the sun generates its energy and how we know what that number is, that lifetime of the sun. So let's get started. Stars are big balls of gas that shine because they are hot. The reason the sun shines actually has nothing to do with the way it produces energy. It shines simply because it's hot. Hot objects give off light. If you were to take an iron rod and put it in a fire and pull it out, it'll be glowing red. It's glowing red and letting off that light simply because it is hot. The other thing that's important to understand is that the sun is letting off energy all the time. This shining of the sun, or its luminosity, is actually a way of losing energy. The action of shining is letting off photons. Photons are escaping the photosphere of the sun. And photons are essentially little packets of energy. So essentially all that light, all that luminosity that we see leaving the sun is energy leaving the sun. Now, there is no heat in space, so the sun is losing all that heat and all that light to space. And unless it has a mechanism inside to continuously produce more energy, it will fade out and disappear at some point. So our goal here is to understand what is that source of energy and how long can that energy last. That's what we're going to try and understand in today's talk. Now, to answer basically that question, how long can the sun continue to shine, we need to understand two things, or answer two questions. The first thing is, what is the internal energy content of the sun? How much fuel does it have? And the second one is, how quickly is it being lost? How quickly are we losing that energy? Think of it in the context of a car. If you have a car with a tank of gas, and you would ask yourself, how long can I drive this car at, let's say, 60 miles per hour? You would have to ask yourself, how much gas do I burn while driving 60 miles per hour? And how much gas do I have? And if I were to take the amount of gas that I have, divide that by the rate at which I'm burning it, I would get the answer of how long I can drive the car. Same thing applies with the sun. It's a relatively simple formula. The lifetime of the sun is simply the amount of internal energy divided by the luminosity. And again, the luminosity is the speed in which the sun is burning its energy. We can actually measure it. It's a very simple measurement. You can actually measure the amount of photons you're getting from every square inch of the sun's surface. Because the sun is a ball, we know how to calculate that surface. It's basic geometry. It's 4 pi r squared. So if you were to take that total surface and multiply it by how much energy or photons you can measure from a single square inch of the sun, you can understand how much energy the sun is burning at any given moment. So if you knew the internal content of the energy of the sun, divided it by this rate of luminosity, with this rate of energy that's being burned, we'll know how long the sun burns. Now, when people started getting really interested in doing these kind of calculations around the 19th century, there were only two forms of energy that we really understood back then. There was chemical energy and there was gravitational energy. Chemical energy was basically what happens when I take heat and oxygen and apply it to, let's say, wood or coal, the process of burning. What is happening in that process by introducing heat and oxygen is that we are breaking up the chemical bonds between molecules. And breaking up those bonds is releasing energy in the form of more heat. That is essentially the process of burning. And chemical explosives, which were already around in the 19th century, are simply an accelerated manifestation of the same process. We're looking at an object which has an accelerant in it. If you think of TNT as an example, dynamite. If we take dynamite, we're essentially accelerating the process of burning, of applying heat and oxygen to the material we're dealing with, and we are releasing a lot more energy instantly in a more explosive way. But essentially, at the core of it, it's the same process. We're simply using oxygen and heat to break up chemical bonds between molecules, and that is releasing energy. So that is what chemical energy is, and people were generally familiar with that. The other kind of source of energy was gravitational energy. And people had a pretty good understanding by that time of how they didn't understand why gravity worked the way it does. They didn't have Einstein yet, but they had Newton, who gave a pretty good understanding of what gravity does or how it interacts. It was nailed down in his formulas and the laws. And people had also practical experiences even long before Newton. I mean, you could, see water running down a hill, and you could build a mill there, and that would the water would turn a wheel, and you could use that energy to do work, to do power, to apply power. There was also another form of gravitational energy when people saw asteroids or comets plowing into the Earth, and all that kinetic energy was changing into heat energy. So these were the basic sources of knowledge that people had for energy in the 19th century. It was either chemical burning or it was, gravitationally driven energy. So basically, they try to use these thought processes to figure out what is the source of energy in the sun based on what they thought energy would be and how long that could last. Now, if you take the most powerful form of burning, I mean, they tried, by the way, calculating what if the sun was all made from a big ball of coal and it was burning coal in space. Forget that there was no explanation of what was the source of oxygen in space to help that burning go on. That question wasn't really being asked, but they were coming up with relatively puny numbers with their assessments of the mass of the sun, and they assumed that there was a ball of coal about the mass of the sun burning. Didn't really produce a long number. So they went with higher explosive energies, and they used the most powerful form of chemical explosion that was known at the time. And they applied that. They took that and said, okay, what if we had the sun literally made of TNT, okay? And all that is burning somehow for a long period of time. And it's producing, so they could assume that there was a certain amount of energy being produced from that process. And they divided that by the sun's luminosity. Remember, this is the rate the sun is burning energy or losing energy.
Can I
And
continue?
when they went from
How can you calculate how long the sun will shine? Do you know
okay,
how the sun
Anas,
shines?
is that a question?
It's very, very hot. Something that is hot shines.
Anas,
Okay, give-
you
Yes.
go could you go on mute because we can all hear you?
Oh, sorry about that.
Not a problem. So so basically we're looking at the total amount of energy that could be produced chemically from very powerful explosives divided by the luminosity, the rate at which the sun was burning. When they put that in that formula we saw earlier on, it produced a relatively unimpressive number. It produced around 16,000 years. And already at that point in time, geologists knew that the Earth was at least 100 million to potentially a billion years old, definitely in the hundreds of millions of years old. And so this created what is known as the age crisis, part one, where what was matching didn't make any sense. We were finding fossils in the Earth illustrating that there was life a million years ago, 10 million years ago, 50 million years ago. And to have life, to have plant life and animal life, we know that we need heat and we need energy from the sun. So how could life and Earth be older than the sun? This didn't make any sense. So chemical burning did not seem to be a good source for energy to operate the sun. And in fact, Isaac Newton postulated many years ago, many years before that, over 150 years before that, that actually meteors crashing into the sun and asteroids crashing into the sun, not meteors, sorry, asteroids and comets crashing into the sun would be a great source of energy. And somebody actually ran the calculations of continuous bombardment onto this ball of gas that is releasing energy. And that could also produce about 1 million years of energy. And that is, again, more impressive than chemical burning, but still nowhere near enough to support life and to support the luminosity of the sun for hundreds of millions of years. This just did not make any sense. So along came two other scientists, and these were Lord Kelvin and another scientist by the name of Helmholtz. And they came at it from a different angle. They said, listen, the sun isn't just a solid ball of some material, it's a ball of gas, and the laws of gas apply to how it operates. And this ball of gas, this incandescent ball of gas, which is glowing because it's hot, is held by a balance of two forces. It's held by the balance of gas pressure. You have a lot of molecules of gas pressing on each other and therefore pressing out. And then you have gravity pressing everything in and trying to pull everything down. And a balance between these two things is what's going on here. So let's try and see what that tells us about maybe using gravity as the source of energy. And what they proposed is the following model. The interior and structure of the star is held by the balance of these two forces. They need to be in what we call hydrostatic equilibrium, the balance between the pressure and the gravity. And as long as it's balanced, nothing is happening, nothing will change. Gravity keeps everything, falling down and is stopping from pressure from tearing the star apart. And pressure, the molecules of the gas are pressing outside and pressing against gravity from completely collapsing the structure. And as long as these two are in balance, we have a stable star in hydrostatic equilibrium. Now, what happens, though, is that at some point, when these forces are in balance, there is no change to the state of the star. But we mentioned earlier on that the sun shines. And as it's shining, well, it's letting off energy. All those photons that are leaving are carrying energy away from the sun, and it's losing some heat. Now, if it's losing heat, ultimately, it's going to lose pressure. And now we get to a point where pressure and gravity are no longer balanced. Gravity has more power or more force left than pressure. And under these circumstances, the star will condense a bit. As it condenses a bit, the sun is smaller, it's more tightly gravitationally bound. And when that happens, what happens is the internal density of the sun goes up. We've contracted it a bit, so everything gets more dense, more hot, pressure increases, and now can balance out gravity. And this process can go on and on. So the model that was suggested by Kelvin Helmholtz was that the sun will lose some energy, therefore pressure will go down, gravity takes over, the sun shrinks a little bit. Because it shrunk a little bit, everything got more dense, heat went up, pressure went up, balances out the star. Now the pressure and gravity are balanced again, and then it'll lose more energy to shining and condense again, and that process can go on and on and on. So we're using the gravitational binding force of the sheer mass of the sun to create more heat and shine off more heat. And they took that model and put it into that same formula we saw earlier. So we take the gravitational binding energy of the sun, which is essentially based on its mass, and we again divide that by the luminosity. And all these numbers, you don't need to remember them. They're not critical for the understanding of today's presentation. But they're basically units of measure of energy. Okay, so we're looking at the gravitational value of the energy of the sun divided by the speed at which it's losing that energy, the luminosity. And now when we plug that into the formula, we get an object that can shine this way for 30 million years just by shining off light, condensing a bit, increasing pressure, shining off again. The sun could operate for 30 million years. But by the time that they did these calculations, geologists on the Earth came to the conclusion that the sun is at least 2 billion years old, or the Earth was at least 2 billion years old, and therefore the sun had to be older. So this was a real challenge. This is the age crisis part 2. Now, at the time, Lord Kelvin, who had a somewhat high opinion of himself, basically said, well, the geologists must be wrong. But obviously we know that they were not wrong. And as we moved into the 20th century, with the discovery of radioactivity, we were able to do a lot more measurements of the age of the Earth, concluding that the Earth is about 4.5 billion years old. So there was no way that the Earth with life on it could be that old and the sun could be that young. We could not have a young sun. So this just didn't make sense again. And what was not known at the time to Helmholtz and to Kelvin was that they didn't know anything about the structure of the atom. That was something that came later. So they did not know that there was a whole new type of physics that stars can tap into to generate orders of magnitude more energy than is available from either gravitational binding or from chemical sources. And that takes us into the next phase of the 20th century. In the 20th century, there was the discovery of nuclear energy, and it evolved over time. It wasn't an overnight discovery. It starts actually very late 19th century with Röntgen and Becquerel discovering radioactivity and the pioneering work done by Madame Curie and her husband Pierre that started uncovering other sources of energy that were coming from within the nucleus of the atom. Then in 1905 came along Einstein with his miraculous year, and among other things came up with what is probably the most famous equation in the world, which is E equals mc squared. And there's many things that we can take away from this equation, but the really two important ones that we want to pay attention to is that matter and energy are interchangeable. I can place them in the different places of this equation. I can turn matter into energy and theoretically energy into matter. And the other thing is that even if I were to plug in a very small amount of mass, even if I put in a very small number in m over here that represents mass, when I'm multiplying that very small number, a little bit of mass, against c, the speed of light squared, I'm going to get a huge amount of energy. So what this equation was telling us was that in matter, there is a whole huge amount of energy that is locked up. The second thing that happened, or the third thing that happened in the early part of the 20th century by, it was a physicist by the name of Eddington, he noticed an interesting aspect that 4 protons, essentially 4 atoms of hydrogen, had just a little bit less mass than one atom of helium. So if I take 4 atoms of hydrogen and I look at 1 atom of helium, they're almost the same weight. There's only a 0.7%. This is less than 1% difference in their weight. But if I were to take that little difference, again, that little bit of mass, and put that into the Einstein's equation, I would get a lot of energy. And so maybe this could be a source. If there was a way to fuse these atoms together and convert some of that mass into energy, maybe this could be a way for the sun to generate energy. Now, let's first of all put some numbers behind this. If I were to take 1 kilogram of hydrogen and I would somehow find a way to fuse it into helium, fuse the atoms together and create helium, I would get 0.993 kilograms. I would lose basically 7 grams of mass. So out of a kilo, I would be almost with a kilo left, just 7 grams left. Now, if I plug in those 7 grams into Einstein's equation, I'm getting a huge outlet of energy. I am breaking the bonds now, not of chemical compositions between molecules. I am breaking bonds at the subatomic level, which releases more than 10,000 times more energy. This number of 6.3 with 14 zeros doesn't really mean much to us. So let's give an example of how much that energy really is. That 7 grams, which is nothing. It's less than I mean, it's not a pencil, it's really heavy compared to that. It's like a third of a pencil. Converted into energy, produces enough energy to take 64 million tons of rock and move it about 3/4 of a mile in the air. That is a huge amount of energy. If I were to take, instead of 7 grams, if I were to take 100 grams, that would be a hydrogen bomb. And 100 grams is still not a lot. That would be a hydrogen bomb enough to level any major city on the planet. Our sun, as it turns out, and we'll talk about that in more detail later, our sun converts 600,000 tons of hydrogen into helium every second. So 100 grams is a hydrogen bomb. We're talking about 600,000 tons converted every second. That is the equivalent of billions and billions of hydrogen bombs going off at the heart of the sun at any given moment. So the question is, it's an interesting theory. How does it work? How do the details of this process work? Before I go any further, by the way, I want to take a quick break here and see, are there any questions? Because we walked through the chemical theory, the gravitational binding theory, and now we're dealing with nuclear fusion theory, and we're going to go deeper into that. But before I go there, let me see, are there any questions from anyone? I'm going to see, I think there's one thing here that came in the chat. Oh, that was just me. Okie dokie then. So I will continue. How does all this work? Okay, sorry, I was stuck there. So the protons don't just bump into each other accidentally. It doesn't work that way. In fact, when we're dealing with hydrogen and we're looking at ionized hydrogen, so it's basically the protons that are smashing into each other. These objects, these subatomic particles, have a positive charge. If you've ever played with magnets when you were a kid, you would take, the two sides that attracted to each other, there was the plus and the minus, and they would stick together. But if you took the other sides, the plus and the plus, or the minus and the minus, they would repel each other. They would actually, you'd feel a repulsion force. Now this force, this electromagnetic repulsion, is extremely powerful. It's in fact 10 to the power of 40 more powerful than gravity. If anyone thinks that gravity is a really strong power, all you need to prove how weak it really is take a small magnet and take a paper clip and attach it to it and stop and think and look at your experiments. You've got planet Earth with its massive big size and all of its gravity trying to pull on that little paper clip to fall down. And yet a little magnet in your hand is powerful enough to offset all of the gravity of all of Earth. That's how powerful electromagnetic repulsion is. So when I have two protons approaching each other, that repulsion is going to move them aside. They're going to not get close. It has to be really dense and really hot for them to overcome that repulsion. And because of that, we find that only about 10% of the sun, the core of the sun, is dense enough where the protons are so squeezed together and the temperature is so high, around 10 million degrees Kelvin, that they can start moving quickly enough and start smashing into each other before they can repel each other because of the electromagnetic repulsion. And they start fusing. This process is called the proton-proton chain reaction. And in the next slide, I'm going to show you how that works. You can kind of ignore the chemical formula on the left-hand side, and we'll just use the chart to follow how this process happens. So in the heart of the sun is mainly made of hydrogen, and there are this sea of protons, of trillions and trillions of protons in the heart of the sun. And we start with 4 protons, basically, again, this is hydrogen atoms, and we smash 2 of them together. Now, when these protons smash together, 2 subparticles are released. One of them is called a positron, and the other is called a neutrino. A positron is essentially a piece of antimatter. So for those of you who've seen science fiction movies and you hear the antimatter chamber is heating up and all that, it isn't science fiction. It's actually real stuff, and it's happening in the heart of our sun. A positron is essentially a positively charged electron. And once it interacts, once it is ejected from this fusion process, it will interact with an electron and self-annihilate, and 100% of that mass will convert into energy. It is the most efficient energy exchange in the universe. So that is one source of energy. And another source of energy is the neutrino, which is a very small subparticle moving almost at the speed of light, carrying a huge amount of energy with it. And we'll talk more about these neutrinos, but they stream out through the sun, carrying energy with them. So we've smashed 2 protons in the heart of the sun. And the first thing that happened was we created an atom of deuterium, which is a proton and a neutron. And in the process, we released energy in the form of a positron, antimatter particle, and a neutrino, which is a very small particle. We'll talk more about them a little later. Then we have this deuterium, which is this proton and the neutron bumping into another proton. And in that process, they will create helium-3. We have now created an atom that has 2 protons and 1 neutron in it, and we've released a gamma ray photon. Okay, so now we've created that photon that is going to carry more energy with it as it eventually leaves the surface of the sun. And then finally, we'll take 2 helium-3 atoms and smash them together. And in the process, it'll release two protons into the proton soup in the heart of the sun, and it creates a stable helium-4 atom consisting of 2 protons and 2 neutrons. So this is the nuclear fusion process that occurs in the heart of the sun, and in all stars pretty much about the size of the sun, or up to about 1.2 solar masses. Above that mass, it's a slightly different process, which we'll maybe refer to when we come around to the talk on the life cycle of stars. So it's the proton-proton chain reaction, starting with protons, creating deuterium, creating helium-3, creating helium-4, and in the process, they're releasing all these massive amounts of energy in the form of positrons and neutrinos, as well as gamma rays or gamma ray photons. Any questions about this process? So far clear, or have I lost people? Okie dokie. I'll take silence as
You're clear.
All righty, cool. So going forward, let's put this to the test. Does this theory make sense? So if I were to take the core of the sun, okay, the fusion of the core of the sun, as you'll soon see, produces more than enough energy to keep the sun going for a long time. But let's put that into the formula. So when I'm looking at the core of the sun, it's only 10% of the sun. I don't need the whole mass of the sun in my formula. I'm just going to look at only that 10% that is involved in the fusion process. And what is the mass that I have there? And again, look at what that energy value of that mass would be. And then I obviously assume that I'm only converting 0.7% of that into energy. So it's not even that whole number, because it's only 0.7% of that mass that'll convert into energy. Produces a big number with 44 zeros. I divide that by the luminosity of the sun. This time, I get an answer of 10 billion years. So now we can see that hydrogen fusion can power the sun at its current level of luminosity for a period of 10 billion years. And because we know that the Earth is around 4.6 billion years, we're assuming that the sun is about a middle-aged sun, somewhere halfway through its life. So that is, you know, the model that's based on assuming that the source of energy is from nuclear fusion. So let's recap on the different energy release comparisons here. The first one was chemical. It was really unimpressive. We saw that it was, you know, it was less than 20,000 years. It was maybe 16,000 years. Whatever you would try and burn, no matter how efficient the chemical burning or exploding would be, it would not power the sun for not even 20,000 years. The other model was the Kelvin-Helmholtz mechanism. And it's one that I'm going to pause on again here, because even though it is not the source of energy for the sun, it actually is a very important mechanism that plays a very important role in the life cycle of stars. And we'll be referring to it multiple times in the talk in January. So that process of the sun losing some energy, or a ball of gas losing some energy, condensing a bit, getting hotter again, and losing more energy, that process actually does occur, and it does have a very important role in the life of stars. It's just not the source of energy that can power it for any materially long period of time. Alone, it would only power the sun for about 30 million years at its current luminosity. However, the proton-proton chain reaction, well, I only need 10% of the sun to allow me to produce energy at the current level of luminosity, at the current rate of losing energy, for 10 billion years. So the key question is, and I'd like to sort of maybe open this to the audience, see if people have ideas, is how would we know? And let me phrase the question this way. When you plug something into your socket at home, you're clearly getting energy. Where is that energy coming from? If you were to follow the power lines and arrive at the power plant, now you're looking at the power plant, how would you know if that power plant is producing energy from burning fossil fuels or from nuclear fusion? How would you tell? Anybody have ideas?
Well, one thing that you could be looking for is neutrinos.
Exactly. So you'd be looking for the byproduct. You'd be looking for the byproduct of the burning. If I were facing that power station and seeing a big chimney stack with lots of air pollution coming out of it, I would know that they're burning fossil fuel. And if I were in front of this building that had nothing coming out of it, but I had a Geiger counter or something else, I might pick up radioactivity. So based on the byproducts, even though I can't see, no one can see what's going on in the heart of the sun, but based on the byproducts coming out from the process, I can test and see, is my theory correct? And as Ken just said, the byproduct we're going to focus on are these electron neutrinos. Now, they're created in this process of the proton-proton chain reaction. What are these neutrinos? Neutrinos are very, very small particles. They are almost massless. They're not massless, but they're almost massless. And they're moving at a speed that is close to the speed of light. And they are beyond tiny. If you were to take a parsec of lead, that is roughly 20 trillion miles of lead. Think about lead, a very, very heavy metal. It has got massive protons, 99 protons in the nucleus of a lead atom. we use them to protect ourselves against radioactivity, right? That's really dense material. And I'm talking about 60 trillion miles of it. And I were to shoot a beam of neutrinos, of 10 neutrinos, 7 of them will come out from the other side as if the lead wasn't even there. That's how small they are and how weakly they interact with matter around them. So, and they don't have any electric charge, so there's no reason for them to interact most of the time, unless there's a direct hit into a proton. They will not interact with the matter around them. So they pass through anything. So the sun is nowhere nearly as dense as what I've just described. Stuff can just pour out of it without any problems. So neutrinos are pouring out of the sun. In fact, in every second of the day, every square centimeter of your body has 60 billion neutrinos just streaming through us. Every day, every second of the day, hundreds of billions of neutrinos are passing through our body from the core of the sun. Within, a few minutes, they just pass through us and we're none the wiser. So they're very small particles. Now, we believe that they're created in the core of the sun because of our theory of nuclear fusion, but if they're so small and they don't interact with anything, how on earth would we detect them? So for that, we've created neutrino observatories. And they're typically, this is one based in Japan. And basically, there are others around the world. There's one, I'm not sure if it's still active. There was one deep in a mine shaft in Minnesota. They're typically built miles below the surface because we don't want the detectors in this observatory to be impacted by any cosmic rays or any other sources of noise that could impact and create a false register. So typically they're buried literally a mile or two below the surface of the Earth. It's filled with 50,000 tons. This specific observatory is filled with 50,000 tons of ultra pure water. And if a neutrino emanating from the sun flies through this and interacts with an atom of this highly pure water, it will release a positron, which will emit a flash of blue light. And in this observatory, there are 12,000 photodetectors that are waiting for those events to happen. And these observatories have been measuring neutrino hits for years. And the data that has come in has shown very clearly that the number of neutrinos that were detected, and obviously we're not detecting all of them. We expect to detect only a small portion of the ones that are just streaming through. But the ones that have been detected are entirely consistent with the rate of nuclear fusion in the core of the sun that would be required to support the sun for about 10 billion years. And there are other ongoing experiments right now that are there trying to get finer results and refine the details. But there is direct evidence that is very supportive of this model of nuclear fusion. So to recap, there were various theories of how the sun can operate and how long it can shine. What we found was that the ones that were based on chemical sources of energy or gravitational binding energy were simply nowhere nearly enough to substantiate a long-lasting sun that would support life for hundreds of millions and clearly now billions of years on the Earth. At the beginning of the 20th century, with more understanding of atomic energy, new models were created that came up with the proton-proton chain reaction, and we've been able to structure experiments that are validating findings that we would expect to see based on what we have hypothesized is going on in the heart of the sun. So let me take a quick break here and see if there are any questions. We'll go now next into a quick overview of the structure of the sun before we come to the end of the presentation. So it's like 1 or 2 more slides. But wanted to stop here and see, are there any other questions from anyone? Okay, so what is the structure of the sun? This is a decent model which is capturing quite a few things here. Obviously here in the center, that very light blue core, that is the core of the sun. That is where that nuclear fusion, that proton-proton chain reaction is occurring. Now, the rest of the sun is still very tight and very dense, and so it is more efficient for energy to pass through radiation. If you think about a pot, and the pot is very hot. It's letting off heat, but it's not changing its shape. It's still shaped like a pot. It's very stable, but it's radiating off heat. As we go further away from the core, we get into what is known as the convective zone. That is like the water in the pot boiling. So that water is bubbling up and down because it has more range of motion, and there is the transition of energy works easier through convection, or through this bubbling effect, if you will, going on in the sun. So we have the core, we have a radiative zone where energy passes through radiation, and then we have the convective zone where it's through motion that energy is being let off. The photosphere, this is, you can think of it as the underlying side of the surface of the sun. This is where we can see, this is first of all where photons leave the surface of the sun. And when a photon leaves the surface of the sun, it arrives here on Earth within 8 minutes. However, that photon may have been created anywhere between 10,000 to well over 100,000 years before in the core of the sun. If you remember that proton-proton chain reaction, that photon that is created is going to bump into other atoms and get absorbed by them, and then leave that and get absorbed by the next one. And it's very dense material. So it can take as much as 10 to over 100,000 years. And I've heard numbers go as high as 300,000 years for light emanating from the core to finally reach the surface and then make a quick 8-minute dash over to us. So, and you can also see, this is where we would see the sunspots, which are areas of magnetic activity on the sun where there might be a slight difference in the temperature. They're not really black as they appear in the images. It's just that if the surface temperature is 3,000 to 5,000 degrees and their temperature, because of magnetic activity and material falling down deeper into the convective zone, might only be 2,000 degrees, they appear darker. It's not that they're not hot, they're extraordinarily hot, and they're not black, but to images that we take, they appear darker because of this temperature difference. And then we have the chromosphere, which is where you can actually see, if you're using a telescope with a hydrogen alpha filter, you can actually see surface details of the convection on the surface of the sun. It's also how you would see prominences, which are materials of plasma, really extremely hot gas in a strange state called plasma, which is not exactly a gas and not exactly a liquid, shooting off from the surface of the sun and following magnetic fields and falling back onto the sun. So these are the main components or the structure of the sun. There is also the corona, which sometimes is referred to as the atmosphere of the sun. It's an area where particles of the sun are accumulated along magnetic lines and achieve extraordinarily high degrees, as much as 1,000,000 degrees, actually hotter than the surface of the sun. And while there is a lot of research trying to shed light on it, it's still a bit of a mystery why the corona is as hot as it is compared to the surface of the sun. So that is pretty much what I wanted to cover. I wanted to share with you a couple of pictures I took of the sun. This one was taken back in 2012 during the Venus transit. And this is a white light filter where you can see some really nice sunspots over here and a really big one over here. This is probably 3 times the size of the Earth, if not more. And over here, you can clearly see the clear-cut silhouette of Venus crossing the surface of the sun. So this was the Venus transit of, I think it was June of 2012. And this is an image that I took during the total solar eclipse in 2017, where this black silhouette is the moon, and behind it you can see we can't see the sun itself, but we can see the corona of the sun and a bit of the prominences shooting out, this little red stuff shooting out from the surface of the sun. And this is the full longer exposure I took of the same event, where you can actually even see some lunar details over here, and you can still see that little flare, that little prominence coming out of the sun. But what is nice here is you can see really the full corona structure that was visible that day. So that concludes my presentation. And again, sorry about the mishap and the transition between the 2 meetings, but I'm glad that we were able to get everyone together and get through the content. I see there was a question that came in about what is known about the neutrinos that reach Earth. So pretty much what I already shared with you is that neutrinos are pouring out of the sun. They're pouring out in a tremendous rate. As I said, if just through your body, we're talking about hundreds of billions of neutrinos pouring out every day. Actually, it's 100 every second. They reach through the Earth and they pass through the Earth. Again, most of it is undetected. The overwhelming majority of it is simply undetected because they have no electric charge, they're almost massless, and they're moving at the speed of light. They just move through everything and continue on into space. With purpose-built observatories, we're able to detect some of the neutrinos as they interact accidentally with those water pools that I showed earlier on, and those flashes of light that creates is detected by these photo detectors that are installed in these observatories. So hopefully I answered that question. I see there's more questions coming in, so people raising their hands. So please go ahead.
Perturbance versus prominence. I'm not sure which is which.
Well, a perturbance is so there's a prominence, there's a perturbance, there's a flare, and then there is a coronal mass ejection. These are all different elements, all of them tied to the same thing, which is this is plasma on the sun. Again, the surface of the sun, it's not a liquid and it's not exactly a gas. It's this plasma material, which has its own set of laws in terms of how it behaves. A perturbance might be just a small change in the structure that is causing a bit of a bump. Whereas a prominence is when you can actually see it shooting out as an arch and then falling out and falling back onto the surface of the sun. A really full-fledged prominence is quite noticeable and has very
dramatic.
Exactly. Then you have a flare, which is basically a shootout of material, which is most of the time will end up falling back onto the sun, but it doesn't create that nice normal arch-like structure.
Okay.
If it is powerful enough and shoots out strong enough to escape the gravity of the sun, that becomes a coronal mass ejection. Now we're dealing with material that has left the sun and is now going to be streaming out in space. And that is sort of the material that can sometimes cause trouble. Sometimes it just will create nice aurora borealis lights, and sometimes it can really mess up transformers and impact satellites and other things like that. So
great, thank you.
We definitely don't like them coming our way. Back in, I don't know if you guys remember, in 2003, there was a massive blackout in the East Coast, and there were tens of millions of people without electricity for many hours. I can't remember if it was a day or a day and a half. That was caused by a coronal mass ejection.
Okay.
Any other questions?
Chanan, this is
Yes.
Ed. I was wondering if you could answer two questions.
I'll try.
One of them you might answer next time, but can you give an indication of what the density versus a radio distance profile from the center of the sun is? I mean, I presume it's very, very high in the center, but does it fall off as the thing goes out, or does it stay very, very high until it gets very close to the edge?
No, actually, the first of all, it differs from one star to the next. First of all, it isn't it isn't a uniform answer for all
Yes,
stars.
okay.
But if you were to look at a star, for instance, that is in a red giant phase, which we will talk about during the next talk in January, in a red giant phase, the envelope of the star is extraordinarily fluffy. It is, you could, I mean, if you could build a plane or a satellite that could withstand all the gravitational aspects and all the heat aspects of the star, it could easily fly through the material. It would not be very challenging. It would be much less dense than water. But the core itself, and especially when you're dealing with when you start creating more complex cores with heavier matter inside, you're eating carbon and oxygen all the way up to iron. Now we're talking to things that could be at certain extreme phases 100,000 times more dense than water. And in an extreme case, just before a supernova collapse, it could be 10 billion times more dense than water. So if you're looking at a star that is at its final stage and about to go supernova, and it's a supergiant, so the envelope of the star is somewhere out in Jupiter, whereas the core is somewhere down, in where our sun is right now, that core at the very final moments could be 10 billion times more dense than water, while the envelope is still quite fluffy, okay? Much less denser than water. Our sun is more compact in its structure right now. And so the core is quite dense. It's probably tens of thousands of times more dense than water right now, and which is still dense matter. I mean, none of us could go through that. There's nothing that could cut through something like that. But it's nowhere nearly as dense as other scenarios. And the envelope is still, the convection zone, and especially the surface, would be relatively, you could pass through it. Again, setting aside all the heat and gravitational things that would tear you apart. If you could ignore those, it would be material you could pass through.
Yes, okay. And then the second question is, how constant is the luminosity of, or how constant has the luminosity of the sun been, or is there a way that we actually know that?
We actually do know that, and it is measured. And first of all, there are cycles. As we all know, there are cycles to the sun, the 11-year cycle that people talk about. And there are minute changes in luminosity. But if you were to measure it over a period of, let's say, 100 years, those changes, if you were to graph it out, it would look pretty much like a flat line. So you could go and zoom in onto a decade and say, okay, there was a bit of a fluctuation versus the other one, but these are not material big changes in the outputs. We're talking about fractions of a percent. That is not going to stay that way forever. As the sun starts maturing, it is and will continue to start getting brighter. So if you were to measure this not over 100 years, but start measuring this over the next 10,000 years or 100,000 years, there would actually probably be more of a measurable impact into the increase in the brightness. And obviously, if you're going to look at it over billions of years, the sun will get significantly brighter over the next 5 billion years. It's just not something that will, not something you can really sense in the lifetime of a person.
Yes, but historically, is there significant evidence that it was significantly brighter or significantly less bright over a 10,000-year time spans or something like that?
I actually don't know the answer to that one. I think somewhere that, that there was some evidence of some changes to luminosity, and I don't exactly know how they were measured. It might have been in plant life impact and fossils, but I don't remember the details, so I don't want to mislead you.
But do you think it's been significant or relatively insignificant in the scheme of things?
In the big scheme of things, it's insignificant compared to how bright. Again, 5 billion years from now, it's completely insignificant. It's not even a 1% change. Where it will be 5 billion years from now is orders of magnitude brighter from where it is right now. But over the scheme of 10,000 years, not really big. Any other questions? Thanks for those, Ed, by the way. In which case, I'll hand this back over to Mike. All yours, sir.
Thank you. That's a great talk.
It was good. Very good.